All right. Well, it's a true honor to be able to begin this talk about exploring distant worlds with the James Webb Space Telescope. I'm Dr. Néstor Espinoza, and I'm an astronomer here at the Space Telescope Science Institute. I think there's no better way to introduce and explore the idea of exploring distant worlds that the concept of our own Earth, this big planet that looks, for us humans, very, very big. That's exactly what we are located right now. This is our current location. Our current location is actually one of the planets out of the 8 or 9 for those of you Plutonian fans out there. So this picture is a different perspective of what our Earth looks like. This is a selfie that was taken by the Cassini spacecraft that was going around in close to Saturn. And this little dot that you see with an arrow, that is our Earth. That's exactly where we are too. This is an image that should make you feel a bit small, but if this is not doing the trick for you, consider the following image, which is a picture of our galaxy. This is not a selfie anymore. We cannot go on outside our galaxy yet to take selfies. But this is a very good model of how our galaxy looks like. And our sun, the star that we orbit around, that is only one star out of the 100 billion stars in this galaxy. If this still doesn't do the trick to see how small we are, consider the fact that our galaxy, this galaxy, the Milky Way, that holds its 100 billion stars, is just one of the hundreds of billions of galaxies out there that are going around in the universe. So this is an actual image. Again, it's not a selfie, but it's an actual image of galaxies out there. Almost every point in this image is a galaxy. And our galaxy, is just one of those galaxies out there. So that's where we are. So this makes you think, right? This is a big universe. There's a lot of stars. Again, 100 billion stars per galaxy and 100 billion galaxies in the universe. That's a huge, huge number. So imagine the possibilities out there. Imagine the possibility of having planets orbiting those other stars out there. Here's a very interesting statistic for you. On average, we know that there's out there in our galaxy at least one planet per star. Think about that the next time that you go outside and look at the night sky. Just pick a random star, and on average, you should be pointing not only to a star, but at least to one planet. Now, we know of the existence as of today of in the order of like 5,000 known worlds orbiting other stars. We call these objects exoplanets. This is short for extrasolar planets, planets that are orbiting stars other than our sun. And the whole concept of this talk is not only tell you about these objects, but also tell you how Webb is exploring these exoplanets out there. Now, Webb is revolutionary in terms of the technology that it has. And to understand how revolutionary it is, I think it's important to understand the concept of our reality out there. So the colors of light that you're observing right now, if you look around you, all the colors that you've experienced in your life, those are just a tiny bit of reality. What I'm showing here is a spectrum of the colors in the universe, and the visible colors, the colors that you see, are only a small fraction of that reality. In reality, there's many other colors out there. Here are some colors that you already know. The radio wavelengths, you probably heard of them. Those are radio waves that are going around that we interact with all day through our cell phones, through communication systems, and so on. And there's microwaves too, which we use to heat up our food. So these actually are colors of light that we have that although our brains cannot capture them, our eyes cannot see them because our eyes are trained to only see visible light. We do interact with these other colors of light, and we do know how to measure them. Well, telescopes like, for example, the Hubble Space Telescope that has been in space for a while now, they are able to see mainly visible colors of light and a little bit of ultraviolet and a little bit of infrared light too. But the James Webb Space Telescope actually enabled us to see a big chunk of this infrared light that is out there. So JWST, this Webb telescope, it's an infrared telescope that can see where our eyes can't. Now, you might be wondering why it is so interesting to see in the infrared, and why did you build a space telescope to look in the infrared? Well, first of all, These wavelengths of light in the infrared are extremely interesting because they are the wavelengths of light in which molecules like carbon dioxide and water out there, which are important molecules in our solar system planets, and in particular for life on Earth, that's exactly where they emit and absorb. So we want to understand those colors of light. But also interestingly, everything that you have around, everything is emitting in infrared. If you look at buildings, for instance, if you look at the floor, and if you look at your favorite pet, everything emits an infrared light. And this is exactly the reason why we needed to send Webb to space. We send Webb to space so it can be far away from the Earth and the Moon, so they wouldn't interrupt the light that we're trying to gather from objects in the universe. Webb is in this 1.5 million kilometers orbit from Earth, this L2 point, and it's kind of co-orbiting with the Earth in its movement around the sun. Now let's jump to exoplanets. So what I want to introduce to you today are what I like to call the JWST greatest hits ever. Of course, cannot do ever because Webb it's been only 2 years since it was launched. So we're gonna give you the greatest hits so far. And of course, I don't have the time to get you through all the amazing discoveries that Webb has done. So I'm going to give you a little taste of what are one of the greatest hits, according to me, of what Webb has done for exoplanet science. Because the greatest hit concept is embedded into the music industry, I decided to bring titles to this thing embedded in music. And the first science hit that I'm going to show you is I entitled it Survivor, which has to do, of course, credits to Destiny's Child. And it has to do with planets that have survived their environment on their crazy stars. To this, I think it's really interesting to introduce our own Earth into this concept. So we see the sun every day, and it looks like a very quiet star, more or less. But this is out to change in around 5 billion years from now in the future. So in 5 billion years from now, what's going to happen is that the field at the center of our sun is going to change. That's going to make the sun to expand, and it's going to convert in what we know of as a red giant star. What this will mean is that it will expand so much that you will, if you survive 5 billion from now, you will see it very, very large on the sky. And actually, as you see in this video, you see the Earth here surviving. Well, there's some models that show that the Earth might not survive this expansion of the sun. It might be that the Earth gets engulfed, and then bye-bye Earth. Now, don't despair. I know this might be a bit disturbing to see, but this is happening in the very, very far future. We're talking about 5 billion years from here. It's beyond our comprehension time-wise. We've only been around for a few thousand years, so we're fine. Humans, I mean. But let me show you to scale more or less what this means. So the sun is something like this. I'm going to put this to scale. And the Earth, it's over here, and it looks very small. These sizes are to scale because it's hard to see the Earth. I'm going to do like a close-up. So this is the Earth. Now, when the sun starts expanding, it's going to leave behind the core, basically, of the sun. There's going to be a big chunk of the mass of the sun embedded into a very, very small ball. Now, how small? Here I'm plotting, again, at the center of the sun. You can see it, this little white dot. That is going to be the core that's going to be left over from this expansion. We call this a white dwarf. It's going to be more or less the size of the Earth. Now, the interesting bit is that we don't know, again, if planets like the Earth will survive. And we don't know if what's going to happen to planets like Jupiter or Saturn or Uranus and Neptune and all the objects out there in our solar system. We didn't have data on this until now. So what I'm going to show you next, it's a very, very exciting result from JWST, which you can actually take pictures of these white dwarfs to try to see if they have planets going around them, which is very, very, very exciting. So I've entitled this potential pictures of planets around these white dwarfs. Excitingly enough, this is work, there's some teams working on this around the world. And one of these teams is led by Susan Maloney, which is actually my office neighbor. And she has a team that has led some imaging of these white dwarfs out there in other white dwarfs that are going around in our galaxy. And here are two pictures of these white dwarfs. So these dots that you see in the center, those are actually these white dwarfs. So these are these future sun. I know they don't look like beautiful pictures of the photos that I just showed, the video that I just showed you. But this is actual flux coming from these white dwarfs. And what Susan and her team have done is to remove the image of these stars in order to see if there's a planet orbiting around them. And she actually has detected what seem to be like planet candidates that they are uncovering with this. Now, these are planets that are very big. We're talking about planets that are like more massive than Jupiter. But still, these are the kind of planets that you're looking for. You're looking for these survivor planets to see what the future might hold to like our own Earth, our own solar system planets in the future. I think this highlights a lot of what Webb can do. First of all, because as I told you before, you need Webb to detect these planets because they're emitting in the infrared. So there's no other way actually to detect these objects. So Webb is very unique in that it can go to these infrared wavelengths where planets like our own are emitting a lot of light, so you can actually detect them. And also, this is the first time that we're doing this kind of science. So seeing planets that have survived this red giant phase of objects out there, it's unheard of. And this is the first time we're gathering like strong evidence about them and learning about what the future might hold for solar systems like our own in the future, which is pretty exciting. The second science hit that I brought you has to do with atmospheres, and that's why I'm entitled this Tell Me How I'm Supposed to Breathe with No Air, which is a song by Jordan Sparks and Chris Brown. There's another reason why I put this name to it, and that this is actually the name of a proposal that was written to JWST to characterize atmospheres of planets out there, which is pretty neat on its own. I don't think there's a better way of introducing the concept of exoplanet atmospheres than our own solar system. And in particular, I think a very big chunk of this is studying, understanding our own solar system rocky planets. And to do that, I brought this ranking of terrestrial planets as vacation destinations. Like, yes, I ranked the planets as your better vacation destinations. And I'm going to get started with that with Mercury and Venus, which are actually the worst planets to go in vacation. So Mercury basically has no atmosphere. It's too hot or too cold, depending if it's night or day. And Venus, on the other hand, is too much atmosphere. It's like too dense and it's too hot and cloudy. So hot and so cloudy and so much atmosphere that if you brought your car to the surface of Venus, it will be crashed up because of the atmospheric pressure. So really, you don't want to go on vacation to these objects. Mars is a little bit better. There's little atmosphere, but it has robots, which seem like a nice entertaining. And actually, they overcome the population right now in Mars. Is basically robots. And Earth, of course, is the best planet to spend your next vacation. It has a nice atmosphere, has Wi-Fi, and it's the atmosphere that is producing the air that you're breathing right now. I think introducing these planets in this way is very important because it lets you pass the message that the atmosphere that these planets have are very, very, very important. All these planets have order of magnitude similar radius and masses, but they have vastly different atmospheres. The beauty is that now we have the technology to actually make this remote detection of atmospheric constituents out there. So we can detect atmospheres of exoplanets orbiting out there. Now, this is really exciting stuff. It has one problem though. Small planets like these ones, like the rocky planets in our solar system, we wanted to see rocky planets out there and detect their atmospheres. They're too small, too faint, and too far away to be directly detected. So we cannot take photos of them. But we can detect their atmosphere through some techniques, very clever techniques that we figured out. The first technique that I'm going to introduce, it's called transmission spectroscopy. It's a very simple concept. It has to do with the fact that molecules have very, very detailed diets. So different molecules like to eat different colors of light. If you are lucky enough to see a planet passing in front of the star, which we know of many of them, when they pass in front of the star, part of the atmosphere will block light from the star as well. Not only the core of the planet will block starlight, but also the atmosphere. When this happens, different colors of light will block different amounts of light. Your planet might look bigger or smaller depending on which colors are being absorbed, of light are being absorbed in the atmosphere. This is the concept of wavelength here, of colors of light. And the concept again is that, for example, water likes to eat light in the infrared, these 2 micron wavelengths. So if you see that your planet is bigger in those wavelengths, then it might be that it has water, because it might look bigger because of the water might be absorbing part of the starlight. So the transit event that you're seeing here, this starlight as a function of, so you measure the brightness of the planet transit as a function of time, you can actually see that you have a deeper transit here at 2.3 microns. So you look for the molecule that absorbs a lot at 2.3 microns, and you might claim, the detection of an atmospheric constituent in here. You also can do the opposite. So when the planets go behind the stars, just before they go behind, you measure the flux from the starlight and the planet's day side. But when the planet hides behind, like plays hide and seek, you only measure the starlight. So you can remove the before and after to get the flux of the planet directly. You can actually measure the flux of the planets. Now, these two techniques have actually been exquisite in getting us compositions of planets in very much detail. So in these plots that I'm showing here, x-axis is wavelength, and the y-axis is this transit depth. And you can see these wiggles indicating the presence of methane, the presence of carbon dioxide, the presence of like a whole rich molecular inventory that we've detected thanks to these techniques. So we're using these same techniques to try to explore small planets too. And by the way, these wide colors of light getting all these molecules, it's a very, very first to us in the exoplanet science. And it's all thanks to the James Webb Space Telescope. So James Webb Space Telescope allows us to get this very, very wide range of wavelengths where many molecules emit and absorb, so that we can detect them with our models here on Earth and with these beautiful observations that Webb is getting for us. I'm typically asked, well, what is the most exciting planetary system out there for you? And my personal favorite is a system that is called the TRAPPIST-1 system. This is a system that it's only 40 light years away. That means that if you throw a ray of light to this star, it takes 40 years to get there. It's pretty near for astronomical terms. And it has 7 Earth-sized exoplanets, TRAPPIST-1b, C, D, E, F, G, and H. This image in particular is fantastic because it showcases the mixture of art with science. You see that planets that are too close, if they had atmospheres like the Earth and had water, the water will be in vapor form, so that's why you see vapor. The ones that are farther away, like TRAPPIST-1G and H, there's ice in the table. But the ones in the center, they might have water, they might have liquid water. We call that zone the habitable zone. It's like the right distance to be from your star. Because you might have liquid water if you had atmospheres like the Earth. But that's a big if. We don't know if these planets have atmospheres or not. This is a very important system, and it's very exciting because it showcases the possibilities of having or no atmospheres in just one system. And this is not only an exciting system for the public, this is actually a very exciting system for the scientific community. So exciting that in total, the entire scientific community has devoted in the order of more than 400 hours of JWST time. That is a lot of JWST time to try to detect atmospheres on these planets. So far, through the techniques that I mentioned before, we know that TRAPPIST-1b likely doesn't have an atmosphere, so it's too close. It's so close that the star bombarding, it's just probably stripped the planet from its atmosphere. TRAPPIST-1c, which is the second closest, is still, the jury's still out on that one. But we're continuing to explore this planetary system. And I'm working with some teams on some of these atmospheres and the other systems. So stay tuned for the near future. Now, this is not the only exoplanet system out there. There's many others out there that are worth analyzing and studying. And in fact, here at Space Telescope, we're starting a concerted effort together with the exoplanet community to try to figure out if other planets out there also have atmospheres or not, and why they might have them, why they might not, and so on. So this is a very, very exciting time to be doing exoplanet science. This is going to be done with both Webb and the Hubble Space Telescope. So it's very, very exciting because it's just the beginning, right? So stay tuned for the next few years on what might come up with rocky exoplanet science for small planet exoplanet science out of these Webb discoveries. So I hope that in this 20 minutes, I managed to shine a little bit of light on what Webb is doing, why it's so exciting. And I think we are in a very, very, very interesting time to be alive. It's a very exciting time to be doing exoplanet science, because we finally have the technology to make these detections, to make the detections of molecules on atmospheres of planets out there, of making these survival detections and so on, of atmospheres, in order to answer the big old question of, are we alone or not? So for any further questions, please feel to reach out, and I hope you've enjoyed this talk.